Hi, in this video, I'm going to go over factoring. So we're going to go over factoring polynomials pretty much from start to finish. So I expect this video should go at least an hour, maybe an hour and a half. And we're going to cover all the way from greatest common factor to factoring trinomials, the special formulas, and then putting everything together. So everything is in the modules there, but I don't talk through it myself. I have my own introduction to it, but then I have other people's videos. So I just wanted to make my own video here where I present everything myself and work through some examples, kind of talking through specific polynomials. So the first thing I would say, what is this factoring all about? So the idea behind factoring, the big idea behind it is, we talked about polynomials. So you just studied polynomials in the last chapter. Polynomials are like the building blocks of a lot of things that we study in mathematics. And polynomials, you can add, subtract, multiply, divide, just like integers. Well, think about how important factoring is when you're doing arithmetic. So when you're first learning, for instance, about fractions, when you're learning about adding, subtracting, multiplying fractions, when you're learning about greatest common factor, least common multiple, all those types of things, those are very important when you're doing arithmetic. Well, we deal with algebra of polynomials. It's the same operations, adding, subtracting, multiplying, dividing. So factoring is polynomials is important just the same way factoring integers is important. So what you're doing when you're factoring is you're, in a sense, trying to undo multiplication. So for instance, if you have, let's say, 9 times 5 makes 45. So then you could also ask, well, if I give you 45, could you figure out numbers that multiply to 45? Now, the obvious thing to say here is that we don't want to include a factorization like 1 times 45, because that's, in a sense, that's not a real factorization, because every integer you can factor as 1 times itself. So what we're asking is there a way you can factor it as two integers between 1 and 45, which is 9 and 5? And in fact, you could go further and say, well, since 9 can be factored as 3 times 3, that means we could really say it's 3 times 3 times 5, or 3 squared times 5. But the point is that you're undoing putting together integers by multiplication. So you're trying to see what are the constituent building blocks of integers. And that's really what's going on with polynomials, is we're trying to see what are the building blocks that put together polynomials. If I give you a polynomial, can you break it down into its constituent parts? And by doing that, we're able to do a lot of operations with polynomials. And if you go on to pre-calculus, what you'll see is that there's a lot of information that we get out of the factors of polynomials. So it's not just about algebra. It's not just about, adding, subtracting, multiplying, and dividing. There's actually a lot of theoretical information that you get, but we're not going to cover that so much in this class. We're just going to go over how to actually factor these. And we're not even going to get into everything with factoring, but this is about 90% of the factoring techniques that you would learn in your mathematical life. So with that said, what I'm going to do is start off by showing you the factoring steps worksheet that I made up, which I did several years ago. I adapted it from someone else, and I took it from another instructor and just made some minor changes to it. And it lays out in a single page everything you need to know from the very beginning all the way to the end, from step 0 to step whatever the last one is. And that'll give you an overview of all the steps that you need to take for every polynomial that you want to factor. And after I do that, I'll show you the worksheets that I give you some worksheets with a whole bunch of practice problems on them with the solution. So this is not like homework that you have to do that you're going to get collected and graded on. But with factoring, it's a matter of practice. And when I say practice, I mean practice. I mean, like, you need to do hundreds of these problems to really get good at them. And the more you do, the better you get. And also the more you do, the faster you get, which is something that I don't think students realize as much. It's not just a matter of practicing the problems so that you are able to factor them, but you really want to increase your speed as well. Because as you go on to, let's say, intermediate algebra, and you go on to pre-calculus, you're going to be factoring so often that if you are not fast at factoring, you're going to be sitting there and taking a long time to do it. So you want to be able to do this quickly. And then after I go that, then we'll actually go into the specific steps, and I'll start at the very beginning of everything and go over where we proceed from there. So let me bring up so this is the factoring steps worksheet. Now this is in, if you go online, it's in the module, it says factoring, putting it all together, I think. So if you go to that module, you can open up this PDF, you can look at it, you can print it out, whatever. But as you can see, it says factoring steps. There's a step 0. Okay, so why don't I start with step 1? Well, it's because there's sometimes on some few polynomials, there's just some kind of housekeeping that you can do just to make your life easier. So it doesn't change the polynomial, but it makes life easier for you. So for instance, if it's a polynomial in a single variable, you almost always want to rearrange the terms in descending order, descending degree. Now, that's not something you have to do, but I mean, that's the way that we're going to be doing these. So that's the way we want to write them. If it has more than one variable, then you know, typically you'll want to have the variables in alphabetical order. You know, so you want x, y, z powers instead of, you know, y, z, x. That's just so that it's organized for you, so it makes sense to you. And the leading coefficient, so that just means the coefficient out in front. It's much more convenient if that has a positive sign. So if it has a negative sign, we're going to factor out the negative. So most polynomials that we do, you're not going to have to do much on this step. So that's why I call it step 0. It's not really the meat of the process. It's not really the main steps that's going on. So next we get to these. So step 1, 2, okay, so I have 5 steps. Step 1, this is something you need to do for every polynomial. You need to at least check it. Now, it doesn't mean you're going to have to do it, but you need to think about it. And this is something that a lot of people will skip over. Even students, when they get to pre-calculus, and calculus, they'll forget this step and it gets them in trouble. You're always going to want to factor out the greatest common factor, or at least check that there is not a greatest common factor to factor out. The main step is step 2. You can see this is definitely the longest. Takes up, you know, the entire screen here. So this is the main step. It's based on the number of terms. So you either are looking at 2, 3, 4, or more than 4 terms. And really, if there's more than 4 terms, there's probably nothing you can do. There's some tricks, you know, there's some slick things that that we could go over that sometimes work, but this is really something, if there's more than 4 terms, you probably are not going to be responsible for knowing how to factor that, and no one's going to hold you to that. So you can just say, well, you know, I'm not going to worry about this. So then it leaves 4, 3, or 2 terms. 4 terms almost always is factoring by grouping, which is basically unfoiling. If you remember foiling, the first, outer, inner, last, that was a way of multiplying 2 binomials together. Now, when you factor by grouping, you're unfoiling. So you're trying to take the 4 terms and see what are the 2 binomials that they came from. This is important, not just because you do it with 4 terms, but also when you have 3 terms, these trinomials, you actually will try and introduce another term to make 4 terms, and then you do that factoring by grouping. So factoring by grouping shows up in the AC method, which is for 3 terms. So that also makes it important. If you have 3 terms, then you're generally looking for one of 2 things. Either it's going to be one of these two special formulas, perfect square trinomial. You always look for that first. Otherwise, then you have this factoring trinomial thing, which there's guess and check and AC. So I'm not going to get too much into these right now. This is really when people spend a lot of time learning factoring, this is kind of what they have to practice a lot, these trinomials. It has to do with the pattern of what numbers you see, the plus and minus signs. It just takes practice getting used to the different patterns that come up. This takes a long time to go through. I'm not going to really spell that out right now. If there's two terms, there's there's these other formulas. So this is if you have a sum and difference of squares or sum and difference of cubes. If it doesn't fall into one of these, then binomials you generally can't factor. So main step here based on the number of terms. Now, after you've done that main step, you should do a step where you'd see if you need to still factor. So remember that we're talking about the example of 45 factors as 9 times 5. You wouldn't want to say, so when we want to factor completely. That means factoring into what we call primes, just like prime numbers. So if I asked for the prime factorization of 45, you wouldn't say 9 times 5 because 9 is not prime. So you'd have to continue and say, well, since 9 is 3 times 3, that's really 3 squared times 5. Same thing here. If you factor a polynomial into more than one factor, then you still want to check to make sure that the factors you have left over are themselves prime. They can't be factored further. Most of the time, that's going to be the case, at least 9 out of 10 times. But there are some small number of cases where the factors that you get, you can still factor further. And you just need to check that. So, and then once you've done that, so either you factored it, great, and you've checked to see that you can't factor further. And if you weren't able to do anything, then you can probably conclude it's prime. Now, there are some cases with trinomials where you can definitely know that it's prime, but there are some cases where you might say, well, I can't figure out anything that works. In that case, it's probably prime. And you can also check, so step 5, you can multiply your polynomials together to check you get the original polynomial. Now, that does not show you that you have the right factorization, because you would need to know that you can't factor any further. But if you haven't factored it correctly, then it'll show up. So if you factor it into wrong factors, then when you multiply it together, you won't get that. So for instance, if somebody tried to factor 45 and they said it was 8 times 5, you could correct them and say, well, no, actually 8 times 5 is 40, not 45. So you haven't factored that correctly. But if somebody factors 45 as 9 times 5, then they could check it and say, well, 9 times 5 is 45. So that's the prime factorization. Now, we just said a second ago, that's not correct reasoning, because you could still factor 9 further. So this is a check to see if you've got incorrect factors, but it doesn't tell you if you've factored all the way. But it's still something you should do. Okay, so that's the overview of everything. So now let me show you now the this worksheet. There's a couple of worksheets here. So this one has, this is another worksheet I picked up however many years ago from another instructor. It's got 30 polynomials on it. There's a good variety in here, from pretty straightforward, simple ones to much more complicated ones. And then there's some at the end that are kind of tricky or clever, that require some ingenuity. But it's a good variety. And then you can see there's also this one. This is from another textbook. And this one is going to have 80, I think it's 80 problems. So there's 80 problems here. So altogether, you got the 30 from here and the 80 from here. That's 110. That's a very good set of problems. If you're able to work through all of these and practice them until you're able to do all of these, you pretty much are going to have factoring down. I also include the solutions here. So you can see here, there's solutions to all these, and then there's a solutions here. Sorry, it's a little, this is like a 10-year-old thing that I was copied from, and I haven't gone back and improved it or recopied it again or something. So it's a little smudgy in places, but you can see it has the factorization. So you can check your answers to see if you got it right. And this is not a homework assignment that you're going to turn in. It's just for you to have a lot of good problems, a lot of good polynomials to practice. All right. So let's talk about GCF. Give me just a minute. So GCF and factoring by grouping. So I'm going to talk through a little bit of this. In each of these sections, I introduced it with a little bit of text. So I'm just going to talk through this. So I talk a little bit about what factoring is. For instance, I say here 3 times 5 is 15. So we're trying to undo that, right? 15 is 3 times 5. The reason factoring is more difficult than multiplication is because you're trying to multiplication is just a kind of step-by-step process. You're given the factors, and there's just a very clear algorithm you can use to multiply them together. You can do it with pencil and paper. There's the multiplication you learned in 3rd or 4th grade. Factoring, though, it's less clear because you're asked to find the question. So you're just given a number and you're like, well, what are the factors? Well, I don't know. You could try stuff, but it's not clear exactly where to start. In fact, there's a lot of crypto technologies that are based on this fact that they will use very large numbers that are products of 2 primes, large prime numbers. And if I give you a number that's a product of 2 large prime numbers, you might know that they're a product of 2 large primes, but it could be very difficult to figure out what those 2 primes are. Whereas if you have the primes, it's very easy to multiply them together. So a lot of stuff with cryptography and internet security is based on prime numbers and factoring. So we're going to start with GCF. Now, what's the idea behind GCF? Greatest common factor. So what is a greatest common factor? Well, think about greatest common factor for integers. So we're looking for a common factor. So something that, for instance, let's look at, say, 12 and 15. So what's the greatest common factor of 12 and 15? Well, that's going to be 3. Now, why is it 3? Well, 3 is a factor. It's a common factor of 12 and 15. But it's also the largest common factor. In other words, there's no factor that's bigger than 3 that divides both of them. And so that's what we mean by common factor. So we're going to do the same thing for polynomials. We're going to look at the greatest common factor of the terms. So for each term, whether that's 2 terms, 3 terms, 4 terms, or 7 terms, you could ask, what's the common factors of all the terms? And then you factor that out. And it's really the distributive property. So for instance, if you have 3x times x plus 2 in parentheses, you can distribute the 3x across. So you learned how to distribute monomial across a polynomial. This is just the opposite direction. We're just trying to go the opposite direction. The difference is we're not just trying to factor out anything. We're trying to factor out as much as we can factor out. So we are distributing in reverse. So there's a number of videos here, so I'd encourage you to watch these, but let me go over some examples of factoring by grouping. All right. Sorry, not factoring, but factoring GCF. We're still at GCF. Just a second here. All right, we're back. So factoring GCF. So let's look at something like 3x squared plus 6xy minus 15xy squared. Okay, so what we're going to do here is we're going to look at all three of these factors, and we're asking what is the GCF of these terms. So what's the GCF of 3x squared, 6xy, and 15xy squared? You don't have to worry about the minus sign because the minus sign is just going to tag along. So really it's just these three. So there's two parts to this. You want to find the GCF of the coefficients. So that means what is the GCF of 3, 6, and 15? And then you have to ask yourself, what is the coefficient of the variable? Sorry, what is the GCF of the variable powers? So in this case, x squared, xy, and xy squared. Now, the GCF of the integers, the coefficients of each of these terms, I'm not going to spend a whole lot of time on that because that's something that we did at the beginning of the semester. We talked about GCF, how to find the GCF. So you have to break these down into the prime factorizations. For each power of a prime, you take the smallest power that you see that is in common with all of them. Now, this case, you may be able to guess what the GCF is. So you may look at this and say, well, it's going to be 3. But let's go down to the prime factorization. So 3 is equal to 3. 6, of course, is 2 times 3. 2 times 3. 15 is 3 times 5. So we got 6. 2 times 3, 15. 3 times 5. I'm actually going to move the 3 over here. So what you do when you're finding the GCF is you look at each prime and you find what's the most that's in common with all of them, which ends up being the least power that you see. But the prime has to occur in all of them. So for instance, you don't get 2 to the first here because 2 doesn't show up in 3 and 5. Really, it's 2 to the 0. So we got 2 to the 0, 2 to the first, 2 to the 0. So we need the 2 to the first. We got 3 to the first. So we need 2 to the 0 because that's the smallest, which is 1. We got 3 to the first there. It doesn't matter which one. 5 to the 0, 5 to 0. So there's no common factor of 5, so we don't get that. So we just get 1 times 3 times 1, which is 3. Now, if we were looking at the powers of 3, and let's say that we saw a 3 squared, a 3 to the 4th, and a 3 cubed, you would take the 3 squared because that's the smallest power. And you do that for each prime and you multiply them all together. Yeah, if you need to remember more about this, go back to the videos, go back to the module from the very beginning, where we talk about, we're going over kind of pre-algebra stuff, and we talk about factorization and least common denominator and greatest common factor. Now we're going to do the same thing for the GCF of the variable powers. Same idea. It's the same idea as the prime powers. This is why I think it's so important to teach students who are learning math, arithmetic, how to do the GCF and LCM with prime factorization. Because I always get this, why do we have to learn the prime factorization? If I look at 3, 6, and 15, I can just tell it's 3, or I could guess 3 and then factor it out and see that there's nothing more. Well, this is the reason. When you get to algebra and you have to use the variable powers, if you understand the prime factorization, if you really understand the process of taking the prime factorization and using the powers of the primes to get the GCF and to get the LCM, then you have absolutely nothing new to learn here. The only difference is it's XYZ instead of 2, 3, 5, 7, 11, or it's ABC instead of 2, 3, 5, 7, 11. So it's no different. So what do we have here? Well, here we've got x to the first, x to the first, x squared. So the smallest power of x that we have in common here is x to the first, right? 1, 1, 2. And then y, since there's really no y here, right? It's y to the 0. So that's just 1. So there's no factor of y, so we don't get that. So all we have really is x. So these two together now make the GCF overall. So the GCF is 3x. So now I can go back up here and I'm going to factor out the 3x. Now, when I do that, I have to go to each term and see what's left over. So I have to divide out the 3x. So you want to see, what's left over. So you can think of it as dividing by 3x, or you can think of it as saying, what do I have to multiply 3x to get this? That's what division is really, right? So 3x, what do I have to multiply 3x to get 3x squared? X. There's x left over, plus 3 goes into 6 2 times, plus I've got a y, and then minus 5, 3 goes into 15 5 times, y squared. Okay, so 3x times x plus 2y minus 5y squared. And there's nothing we can do with that trinomial because it's got two variables. It's a quadratic in one and linear in the other. So we can't factor x plus 2y minus 5y squared. So this would be the factorization, the complete factorization. Now, on most problems, what'll happen is you'll have the GCF, so you'll have to factor the GCF, but then there'll be something after that. So then you have to still do a trinomial pattern, or you have to use a special formula or something like that, or grouping or whatever. So sometimes it's just GCFs, but usually it's GCF combined with something else. Okay. Okay, if you give me just a minute. No. I'm just going to bring up some practice homework problems there. All right, so this is homework 40. And let's see. Okay, so I'm going to skip through some of these at the beginning. There we go. Okay. So 12x minus 16. Now this is really the simplest kind of GCF. It's just a linear binomial. So the only part that we can really factor out is the numerical coefficient part. So what is the GCF of 12 and 16? 12 is 4 times 3, 16 is 4 times 4. 3 and 4 have no common factors. So once we factor out a 4, that's all that's going to be able to be factored out. So we factor out 4. 4 goes into 12 3 times, goes into 16 4 times. So factor out a 4, and what's left over is 3x minus 4. Notice that you can always check this by distributing. So if you're not sure you've done this right, distribute through. If I distribute the 4 across, what would I get? I'd get 12x minus 16. And then just make sure that there's nothing else that can be factored. So check what's inside the parentheses here and make sure that you haven't missed any other factors. There's a similar thing here. There's y squared in a constant term. So there's no way that we're going to be able to factor out anything other than the numerical coefficient. So 18 and 24, those have a GCF of 6. So I'm going to factor out 6, 3y squared plus 4. Notice that would give me 18y squared plus 24. Now, this binomial here actually might factor. I mean, it has the possibility of factoring because it's not a linear binomial. If you have a linear binomial, it's never going to factor. But because this is a degree 2, it's a y squared, there is a possibility that it could be factored. We'll see later that there's this formula called the difference of 2 squares, which does allow you to factor some of these. But this is not a difference of 2 squares. It doesn't fall into that pattern. So there's nothing more we can do here. We're just going to leave it 6 times 3y squared plus 4. Okay, I'm not going to do every single one here. Actually, let's look at this one. So if you want to pause the video or just take a minute here, see if you can factor this. This one has numerical and variable powers to factor out. All right. So since 6 goes evenly into 30, right, 6 times 5, 6 is the GCF. You can't get anything, if 6 is one of the coefficients, you can't get anything bigger than 6 as a GCF. So factor out 6, but also we've got x squared and x to the 4th. So remember, you take the smallest power that you see, because that's the most that's going to be in common. Out of x squared and x to the 4th, I need to take out x squared. You can almost think of it as, you know, the powers you can think of like you have different groups of people. Say you had different, I'm trying to make an analogy, different departments on campus, the math, physics, English, whatever. And let's say that you wanted to make new committees. So you have the departments, you want to make committees that have at least one person from every department. Well, you're only going to make as many committees as there are people in the smallest department, because as soon as you do that, you're going to run out of people in that department. So the departments here are like the terms. So this is like saying I could take one factor of x from each of these to make like a committee, and I'd have one factor of x left over there and 3 there, and I could take another one, so I could get 2, but then there wouldn't be anything more in the first term. And that would be it, and I couldn't do any more. So that's why it's 6x squared. I'm left with 5, just 5, because I don't need to multiply any power of x. And then minus, now I'm missing an x squared. So it's 6x squared times the quantity 5 minus x squared. Yes, times 5 minus x squared. Okay, now there's some here where, let's see. So these are trinomials. Now, normally with trinomials, after we after we study trinomials, your first instinct is going to be to run in and try and do the AC method or something like that. Okay. Well, and these ones, there's none of that. It's just saying do the GCF. So out of these, what's the GCF of 5, 15, 25? Since 5 is a common factor of 15 and 25, 5 is the numerical part to factor out. And the smallest power, again, is x squared. So we get 5x squared. And then it's 3 minus, what do we have? Sorry, it's 25x cubed. So 5x, and then plus x squared. Now, normally you would write this the other way around. So you would write these in descending order. So you'd rearrange the terms and write it as 5x to the fourth minus 25x cubed plus 15x squared. So in this case, then you would get 5x squared times x squared minus 5x plus 3. Okay, no big deal. It's the software is not going to mark you wrong, and generally I wouldn't. But it would be normal to write it more that way, the second way. At this point, once you've learned all the factoring techniques, you need to check to see if this trinomial factors. Now, it turns out it doesn't. And if you've seen even a little bit of factoring before, you may understand why that happens. You can't unfoil this. There's no way you can write this as a product of two binomials. So that's it. So we're done here. So I'm going to do it this. I'm actually going to change the order here. Now it should definitely accept this. Yeah. The order of the terms does not matter. This is an example of one where I said the step 0. Remember I said the leading term, you generally want to have positive. So if the leading term here is negative, I want to factor out a minus as well. So normally, if I don't look at the signs, it'd just be 24 and 56. Well, 24 and 56, those, let's see, what is the GCF of those? 24 is 4 times 6. So that's 2 cubed. Actually, it's 8 times 3. 2 cubed times 3. 56 is 7 times 8. 2 cubed times 7. So these are both divisible by 8. And then we got 3 and 7 left over. So there's nothing more. So the GCF is 8. So normally I would factor out 8. But because it's minus 24x squared, I'm actually going to factor out a negative 8. It just makes the appearance, it makes the convention for what's left over better. So when I do that, now I get a 3x squared, because that will multiply to negative 24x squared. And then the positive 56, I have to change the sign, because if you factor a minus out of a positive, you get a minus. So that's going to change the sign to minus 7. So it's negative 8 all times the quantity 3x squared minus 7. And again, you can distribute through to check to see that you've done this correctly. Okay. Okay, this is starting to lead into factoring by grouping. So let's look at this. Now, this one is a little bit different. It's not that it's just like powers of x, y, and z. We've got this quantity x plus 2 in parentheses. So what are we going to do with that? Well, treat it like it was a variable. If I think of x plus y like it was x plus 2, like it was y or z, then I could think of it as a whole thing being raised to different power. In fact, I could see that the x plus 2 actually is a common factor. This is what factoring by grouping is based upon. So it's really important that you get this. X plus 2 is a common factor. Actually, let me go to the whiteboard. Okay, so we're looking at this. So what I'm saying is this x plus 2 in parentheses, right? X plus 2 is itself a common factor. Now, it looks a little weird because you're used to factoring out, number integers like 2 or 5 or 12, or x or y squared or something. You're not used to factoring out quantities in parentheses, but still, it is something that can be factored out. So let's do that. If we factor out x plus 2, what is left over? There's a factor of x there, and then there's minus 17. So what we're left with is x plus 2, x minus 17. Now here's the key when we get to factoring by grouping. If I had just given you x squared minus 15x minus 34, it's not clear exactly how this factors, although you can see if you look above, you can see that the x plus 2x minus 17 that we got, that's exactly how x squared minus 15x minus 34 factors. But how would we get from here to here? That's not clear. So that's what the AC method, what we're going to spend so much time on, is how do we get from there, to there? Now, there's a process we can go through that's step by step. And what it essentially says is we're going to rewrite this term. So I would rewrite this term as x squared plus 2x minus 17x minus 34. So, sorry, it should look like this. So notice I've split up the negative 15x into two terms in this weird way. Now, normally you try and simplify things in algebra, right? You don't take a term and make it more complicated and write it as two terms. But that's what we want to do here, because once we do this, then what we'll see is that we can take these two terms here. Notice that just these two terms on their own have a common factor of x. So I could factor it as x plus 2. And then I could look at these two terms here, the negative 17x minus 34. Those have a common factor of negative 17. So I could factor out negative 17, and I'm left with x plus 2. And that's what I have, notice, that's what I would have up here. So we're kind of in the middle of an AC method problem. Now that we would get it, we got it to look like this. Now we could go through and we do this last little step of factoring by grouping, and then we're able to get that's how the trinomial factors. But this is giving you a peek ahead into what we're going to do in the next couple sections. So this is, in any case, x plus 2x minus 17. And you know what I think I'm going to do? We're already going so long on this. Instead of doing this as one video, one whole Zoom recording, I'm just going to do a separate one for each one, and I'll put the link to it. There's no point in putting it all in a single one and then having to have you figure out the timestamp or figure out where it is in the video that you should be starting. So as soon as we finish the factoring by grouping, I'll stop the recording, and then I'll just make another one for each additional module. Okay. Now this one's a little interesting. This looks the same, but it's like kind of different. 6x times 5x plus 7, and then plus 5x plus 7. So at first, if you look at it as three terms, like there's this big term here, and then there's a second term of 5x and a third term of 7, you might think, well, it's not much I can do here because there's not really a common factor, but there is, because it's 6x, 5x plus 7, And then it's really plus, and then what we can do is group the 5x plus 7 together. So if you put parentheses around that, it still that maybe doesn't look like you recognize what to do here. But now, what if I wrote this as plus 1 times? Now notice, now this does look like, so if I wrote it as 1 times that. Because now, think of 1 just like any other number, like 4 or 13, whatever. Now you can see how I do have that 5x plus 7 that I could factor out. And I'm left with 6x plus 1. Now, you don't want to go through and actually write this every time. You want to just be able to recognize, oh, there's a 5x plus 7. Mentally think of the parentheses around it. And then think that when you factor out the 5x plus 7, you just have the 1 left over, because when you factor out something from itself, it leaves 1, not 0. It leaves 1. But that's the way you want to think about this. So this factors then is 5x plus 7 all times 6x plus 1. We should be getting into factoring by grouping. Okay, so let's look at this one. I'll go to the whiteboard. We got a x squared plus 7x plus 6x plus 42. So the way factoring by grouping works, let me just do this maybe on the side over here. I already mentioned that factoring by grouping was like unfoiling. So you think about the steps that you do when you're foiling. You're just going to do them in reverse. So the first thing is you're going to group the 4 terms into 2 pairs. So you could just take like the first 2 terms and the last 2 terms. Then you're going to look for a GCF in each pair, but separately. Okay, that's key. So when you look at the first 2 terms, you try and find a GCF from those. You ignore the last 2. And when you look at the last 2 terms to find a GCF, you ignore the first 2. So now let's say that you've been able to do that. So you got your GCF from the first, you got your GCF from the second 2. Then you look for a GCF from those factored pairs. And then you factor out that GCF. And then if you can't do this, so just the last thing, if you can't do this, you can try rearranging the terms. When you have 4 terms like this, there's basically 3 ways you can rearrange them as far as teams tennis, is what I say. So if you have 4 people, A, B, C, D, how many ways can 4 people play teams tennis? At first, you might think, well, there could be a lot of different ways they could do it. But really, there's only 3 ways. Because you can just look at who is A going to team up with. A is either going to team up with B or C or D. Because as soon as you determine who A's team tennis partner is, why am I talking about teams tennis? Well, you'll see in just a second. As soon as you determine who A is playing with, so you could have A and B versus C and D. If A is playing with C, so if A and C are a team, then you have A and C are going to play against B and D, or you can have A and D playing against B and C. And that's really it, because now if you try any other possible combination, like let's say that you go to B, you say, well, what if B was playing with something? Well, if B is playing with A, we already got that covered, because the order of A and B doesn't matter. When your teams, the AB team is the same as BA. If you go, well, what about B and C? Well, I already got that covered over here. So all the possible combinations here. So there's only 3 ways you can do this. So if you can't do this, try the other 2 ordering. So try to reorder the pairs. And what will happen is 99% of the time with these factoring by grouping, 2 of them work and 1 of them doesn't. So really, if it doesn't work, you could just try either one of the other 2, and that will work. So an example here would be, let's say that instead of this, let's say that I put it this way: x squared plus 42 plus 7x plus 6x. Now, let me show you, if I try and do factoring by grouping this way, what's going to happen? So I look at the first 2, look at the second 2. These 2, yeah, okay, I can factor out an x, 7 plus 16. These just combine to make 13x. But these 2, there's no GCF. Or maybe a better way to say it would be the GCF is 1. So we can't really factor any GCF out of these. So now I've got x squared plus 42 and 13x. This isn't getting us anywhere. So what you have to do is look at a different order. The other 2 possible orders would be x squared plus 7x plus 6x plus 42, or x squared plus 6x plus 7x plus 42. Either of those will work. Now we're looking at this one, the first one, 7x plus 6x plus 42. So in that case, now when we do factoring by grouping, we look at these 2, we look at these 2. So I factor this. There's a GCF of x squared and 7x. I can factor x out, x plus 7. Here I can factor 6 out, x plus 7. Now notice this is what I was talking about before. Now the whole x plus 7 is itself a thing that you can factor out. This is a GCF. So I factor out x plus 7. What am I left with? Well, I'm left with x plus 6. So that's how this factors: x plus 7 times x plus 6. Okay, if you want to pause the video or take a minute, see if you can factor this by grouping using the same steps that we just went over. All right. Yeah, so if you need more time, you can go ahead and pause the video. So the first 2 terms, x cubed, a 2x squared. So from those first 2 terms, we could factor out x squared. We're going to be left with x minus 2. From the 2x minus 4, there's a common factor of 2. Well, that's it, just 2, but that's fine. Plus 2, and what's left over is also x minus 2. Notice that the factoring by grouping only works kind of if what's left over ends up being the same. If I tried to factor this and I got x minus 3 or x minus 4, now suddenly the factoring by grouping is not going to work here. So just because you have 4 terms doesn't mean you can factor it by grouping. Let's be real clear about that. It has to be of something that can be factored. This is just saying if it can be factored as the product of 2 binomials, then this is the way to do it. It doesn't say that you can always do it. Okay, so now we've got this, and now we want to factor out that x minus 2, and we're left with x squared from the first term and 2 from the second. So x minus 2 times x squared plus 2. All right. Okay, so there's some more examples here. Maybe we'll do one more. Let's see. Okay, let's do let's look at this one. Okay, so actually this one is just a GCF one, isn't it? Yeah. No, let's do this one. So we'll finish up with this one. Now this one has 3 variables. So far we've only seen ones with 2, but it's the same idea. It doesn't matter how many variables it has. If I look at the first 2 terms, t squared minus at, there's a GCF of t. So let's try that. Left with t minus a. And then from the second 2, minus bt plus ab, I could factor out a b plus b. Or actually, let me factor out a minus b. So again, you can factor out the opposite of something if it turns out to give you what you need. So if I had done plus b, what I would have gotten is minus t plus a. And I might stop here and think that I'm stymied because I look at this and I say, well, I got t minus a and minus t plus a. Those aren't the same, so I'm stuck. I can't really do this by grouping. But remember, t minus a and minus t plus a, those are just off by a minus sign. They're opposites of each other. So if I had factored out a minus b instead of a plus b, or if I recognize that I can just factor out a negative, that will change minus t plus a to t minus a. And now I do have that common factor of t minus a. So t minus a, t minus b. And that's the factorization. All right, so that is the overview of factoring, an introduction to it, what's the big idea, everything we're going to be going through, and GCF and factoring by grouping. So we've covered a lot here. What we're going to talk about next is the main part of what often you spend a lot of time on, which is the trinomials. So we'll talk about what do we do if we have 3 terms and we're trying to write this trinomial as a product of 2 binomials. Is it possible to do that? When can we do it? How do we do it? That's going to be the big question. Okay, so I'll see you in the next video where we go over that.